Last episode, we trained our first thing by hand. We wrote out the prediction, the loss, the gradients, and the update, every single line ourselves. It worked. We watched the loss drop and the line snap onto the data. But honestly, it was a lot of bookkeeping for a straight line. So here's the deal for today. We're going to fit the exact same line, get the exact same answer, and we're going to do it with about a tenth of the code. We descended by hand last time. Now we let PyTorch carry the bucket. Here's the thing we kept doing manually. We held a weight, we held a bias, we wired up their gradients, we wrote the update math. PyTorch has a name for a bundle of learnable pieces, plus the rule for how data flows through them. It's called a module. And almost everything you'll ever build, a single line, a deep network, a full GPT, is just a subclass of one base class, nn.Module. A module has two jobs and they live in two methods. In init, you declare the pieces, the layers, the learnable parts. In forward, you describe the data flow, take the input, push it through the pieces, hand back the output, declare the parts up top, define the flow below. That's the whole contract. And the first piece we'll declare is nn.linear. This is just y equals wx plus b. The same line from last episode, except PyTorch creates the weight and the bias for you, fills them with sensible starting values, and wires them for gradients automatically. No more requires grad by hand. No more remembering to track them. You ask for nn.linear, one input, one output, and you're done. But here's the real payoff for subclassing module. Once your layers live inside it, one call, model.parameters, hands over every learnable tensor in the whole model. You don't list them, you don't count them. Whether it's 2 numbers or 2 billion, parameters finds them all. That single call is the reason we bother wrapping things in a module at all. It's the handoff to the optimizer. Next, the loss. Last time we typed out mean squared error ourselves. PyTorch gives it to you as an object, nn.mse loss. You make it once, then call it like a function, give it the prediction and the target, get back the loss. And it's a menu. Today it's MSE loss for regression. Soon it'll be cross entropy loss for predicting words, which is exactly what our tiny GPT will need. Pick the one that matches the job and call it. Then the optimizer. This is the piece that owns the update rule and the learning rate. We hand it model.parameters and a learning rate, and from then on it knows how to nudge every weight. Last episode we wrote w minus equals lr times w dot grad ourselves. Now optimizer.step does that for every parameter at once. SGD is the plain version. Later you'll meet Adam, which is smarter about the step size. Same socket, fancier plug. And here's the loop, the part you'll write for the rest of your life. 3 lines in this order. 0 grad, wipe last step's gradients because PyTorch adds them up by default. Backward, fill in fresh gradients for this batch. Step, let the optimizer take the step. 0 backward step. That rhythm is identical whether you're fitting a line or training a language model. Learn it once here, use it forever. So that's the grown-up loop. One quick teaser before the code. A single nn.linear is quite literally one neuron. A weighted sum plus a bias. It can only ever draw a straight line. Next episode we stack a few of them, add a little kink between them, a non-linearity, and suddenly we've got a real network that can bend. That's the MLP on real data. Okay, the code, it's short, about 20 lines of real content, and I want you to notice how much less there is than last episode's by hand version. Same imports up top, a tiny model class, 3 setup lines, the loop, and then we print what it learned. It runs just over a page in the editor, so we'll turn the page once partway through. Let's walk it. Top of the file, we import torch and pull in torch dot and end as nn. That's the namespace with module, linear, and the loss functions. Then we make our data. X is the inputs, Y is the targets, built so the true relationship is y equals 2x plus 1. We're keeping the data identical to last episode on purpose. Same problem, new tools, so the answer should match. Here's the model. Class linreg, subclasses nn.Module. In init, we call superinit first. Never skip that, it's what registers your layers. And then we declare one layer. Self.linear equals nn.linear, 1, 1. One number in, one number out. That's our whole model. And forward. It takes x, returns self.linear of x. That's it. Push the input through the linear layer and hand back the result. You never call forward directly, by the way. You call model of x, and module routes it through forward for you. Notice what's gone. No manual w, no manual b, no handwritten w times x plus b. The layer holds all of that. Set up 3 lines. We make an instance, model equals linreg. We make the loss object, lossfn equals nn.mse loss. And we make the optimizer, torch.optim.sgd, handed model.parameters, and a learning rate of 0.1. Those 3 lines replace a whole block of manual setup from last time. That's the bottom of page 1. Let's turn to the loop. The training loop, 100 epochs, each pass, pred equals model of x runs the forward pass, loss equals loss of n of pred and y scores it. Then the 3 sacred lines, optimizer.zeroGrad clears old gradients, loss.backward computes new ones through the whole model, optimizer.step updates every weight. And every 10th epoch, we print the loss. Watch what happens. At this learning rate, the loss doesn't crawl down, it falls off a cliff. 12.5 at epoch 0 and basically solved under 100th by epoch 10. 4 clean points on a straight line, don't put up much of a fight. Last block, we inspect what the model learned. Model.stateDect is the dictionary of every learned tensor. And there's our weight sitting at about 1.996 and our bias at about 1.01. 2 and 1. The same answer we ground out by hand last episode, except this time the whole thing is about 10 lines of model and 3 lines of loop. That's the toolkit doing its job. Next episode we take this exact nn.linear, stack a few of them with a kink in between, and build a real neural net, an MLP, on real data. See you there.